two bottles, I expect the level of the water. This is just water, and to just make it color, I have added a little KMNO4 in it, potassium permanganate. So that is so this is not blackberry juice. So it's just water with KMNO4. Okay. So now, my question is that if I want that the level in the two bottles should become equal, first you think why it is not equal. Probably your answer will be that these two bottles are capped. Is it so?
Yes.
Do you expect the levels to be equal when the bottoms are connected?
It depends upon the pressure.
What have you learned about the Pascal's law?
Equally
Yeah, equally or this is also an outcome of the Pascal's law, that the pressure in both the bottles is H rho g or HdG. So now my question is, which cap out of the two bottles should I open so that water flows from this bottle to this bottle?
The orange.
The blue one?
The orange.
Or should it be the orange one? Okay, who likes orange? Please raise your hands. And those who like blueberries, I think you will be liking the blackberry more. I'll leave you with this question. When you will come back, please, I'd like to have your answers.
Okay.
So we'll be joining again after a little break of how many minutes?
So both of them.
So you have thought well during your lunch. Let's first try with the blue one.
It's not going. It's not going. So both of them.
Not going.
No.
Are you little susceptible about that I might have put something in the pipe?
No.
This might have been blocked, isn't it? Possibilities are there. But let's do it right now. So at least I have not blocked the pipe. I have not cheated. So now, you see ultimately the water levels will be same in both the bottles. Okay?
Yes.
So a few of you have been able to get the correct answer that I should open both the caps. Then the water will flow from one bottle to another. Can you explain me why it didn't work with one cap opened?
There would be no equal atmospheric pressure.
Yeah, that's true. But about when I opened this one. Okay, let's start with the oranges. So when I opened the orange cap, water still did not flow into this bottle. Why it was so? I had atmospheric pressure in this bottle. Now, in the bottle with the blue cap, that means it will occupy some volume in the bottle. Do you agree with me? When the water in this bottle goes into this bottle, when it will reach this bottle, it will occupy some volume. And the volume which it will occupy in this bottle, by that much the air inside the bottle, because air cannot escape out of this bottle, so the air inside the bottle will get compressed. And you know, when air will be compressed, it will increase the pressure in this bottle above the atmospheric pressure. Initially the air in this bottle was at atmospheric pressure because when I capped this bottle, the air inside it was atmospheric pressure. When the water rushed a little in this bottle, it decreased the volume of the air and then it compressed the air, and because of that the pressure in this water was higher than the atmospheric pressure, so it did not allow the water to come from lower pressure to higher pressure. This is a natural tendency of liquids to go from higher pressure to lower pressure. When I closed this one and when I opened this one, this was okay at atmospheric pressure, and if you have observed very minutely, a little amount of water came out of it and then it stopped. Now when water came out of it, the air in this bottle has a larger volume to occupy. When it has a larger volume to occupy, the pressure inside this bottle will decrease. Here I have atmospheric pressure, so again it cannot go from lower pressure to higher pressure. Because then when I open this, very little water will be able to come to this bottle, which will decrease the pressure above the surface of the water in this bottle by giving it more volume to occupy, decreasing the pressure, that is your gas loss, and then again water cannot go from lower pressure to higher pressure. So that is how you relate atmospheric pressure with vacuum. When you are lowering the water column in this bottle, you are creating vacuum in this bottle. Now, you know this formula, that is simply Pascal's law. And, I just forgot, who gave me the answer that we should open both the caps, honestly? I heard it from someone. Raise your hands. So you will earn few toffees for you. Dr. Rakevich?
Sure, sir.
I think you like sweets after lunch.
Yes, sir. Thank you, sir.
You will be all given the toffees, but I think let's start with the winners only. Consolation prize will be given to all of you. If I have a few vessels, say of different shapes, and if I fill them up to equal heights, say, then what do you expect the pressure of the liquid at the bottoms of these vessels? Liquid is same, say water in all the three vessels. The area here is smaller, here it is larger, and here it is say still smaller. I have vessels of different shape having different bottom areas, but the water column in all the three vessels is same. So what would be the pressure here? What will be the bottom pressure here, and what will be the bottom pressure here? Given density of water is say D, if you want to stick with D, let it be D. Would the pressure be same in all the three cases?
No, sir.
Why? Because you have larger amount of water here?
Because of the area. Because of the area.
Because of the
area. Smaller the area, more the pressure.
Okay. If it had been so, I should have area in this expression. What this expression stands for? It stands for the pressure at the bottom of a liquid column of height h having density d, isn't it?
Yes.
I have omitted the derivation because you are already done with the derivation part. It does not include area. It only depends, the pressure, the expression of pressure involves only the height of the liquid column, its density and G. And don't you think height is same for all the three vessels?
Yes, sir.
I have taken the same liquid in three vessels.
Yes, sir.
Water, density is same in three liquids. G, definitely G doesn't give privilege to any one of them. So it's same for all the three. So pressure in all the vessels is going to be HdG, and it is going to stay same for all the three vessels. This is something which is known as hydrostatic paradox. What is a paradox? What is a paradox? Literal meaning of paradox, which is against your common sense. Your common sense says that the pressure should be different, but it comes out to be same. How can I prove that this pressure is same? Very easy. I connect the bottom of the three vessels. If the pressures were unequal in the three vessels, then the water will flow from one vessel to another.
Yes,
I have just proved with the last activity that liquid moves from higher pressure to lower pressure. That means if the pressures will be unequal, then the liquid will flow from one vessel to another, and it doesn't happen. That is basically one outcome of Pascal's law. This expression is an outcome of Pascal's law. So this is known as hydrostatic paradox. This is something which my common sense doesn't tell me, but actually it happens. I have collected the vessels with different bottom areas. Dr. Rajesh, please. I can take this one out now. So please focus on this. You see, these are the vessels with different areas. This bottle is not capped, so this is at atmospheric pressure. I performed the last activity to give you an idea. You see, are the levels in the different vessels equal?
No.
Does it violate this principle of hydrostatic paradox?
No.
Who says no? This principle says that the pressure in all the vessels should be equal. Therefore, the height of the liquid in all the vessels should be equal. All are at atmospheric pressure. I deliberately filled them to the different levels because now with the help of the last activity you should be able to make it out that why these are not equal. Because these are capped. The pressure upon the liquid surface here in this hydrostatic paradox is atmospheric pressure, and hence pressure above the surface is equal, whereas in these bottles we have different pressures because of the different height of the air columns above the liquid surface. I have deliberately done it, and this is not in violation of hydrostatic paradox. You will see as soon as you see again the water is not coming into this bottle because a little water has collected here, and after that the pressure in this vessel has decreased, thereby not allowing the liquid to move from lower pressure to higher pressure. This is being at atmospheric pressure. How do you think the levels will become equal? Should I open this cap? All the caps. That's very good. You have learned from last activity. Until unless I will open all the caps, the liquid will not try to retain the height. And you see that these are all junk bottles. I still am convinced that to make activities you don't require. Are the levels coming up and down?
Yes, sir.
So you see, I have the vessels with different base areas.
Yes, sir.
And liquid is trying to occupy the levels. So that means that Pascal's law and hydrostatic paradox is okay. I have kept this bottle. This pipe is above the liquid level. That is why the liquid is not rushing into the last one. If I tilt it a little, it will start rushing into, because then I will be increasing the height of the column by tilting it. So, have you understood about hydrostatic paradox?
Yes, sir.
Have you seen the proof of it?
Yes, sir.
So, that is how Pascal's law works. Now let's come back to the same. Now, have you thought about this activity? Let me show you how I can do it. So I turn upside down, and do I have my torch here? So for that, you will rotate it like this. Honestly, did any one of you thought that this is going to happen this way? So now the question related to the activity. Why I rotated it, when I rotated it, why did it start coming down immediately? Have you observed something in the bottle when it was coming down? Please focus on the bottle. I'll tilt it upside down once again for you, just to observe